This is the lesson on the fundamental counting principle and permutations. To understand permutations, you've got to be able to understand what factorials are. If you ever see something like a number and then an exclamation point, that reads n factorial, or say it was a 5 factorial. That represents the product of all the integers from 1 up until whatever the number was. So take, for example, 2 factorial right here. That would say 2 times 1 equals 2. 3 factorial, 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1, and so on. So let's try one of these warm-up problems together. Let's say we wanted to look at 6 factorial, just problem number 1 right here. 6 times 5 times 4 times 3 times 2 times 1. And then we would just multiply those all out to get our solution. Notice that one special property of factorials is right here. 0 factorial, by definition, is equal to 1. That will always be the case. So if you come down here and look at, say, problem number 9, 3 factorial times 4 factorial times 0 factorial, well, 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 2, times 2 times 1. And then 0 factorial is just times 1, which doesn't really change anything, because anything times 1 remains the same. But that's how we would treat that 0 factorial. At some point in life, you may be faced with a situation where you want to know the number of possibilities for a given situation. That's what we're going to figure out today. Now, there's a few ways to do that. A tree diagram, so what we're looking at right here, is one way to do that. The strength of a tree diagram is that you can see all the possibilities. The weakness is, say there's a lot of choices, a tree diagram becomes a very big diagram, and so it's not always the best way to go. Let's say, for example, that you have an ice cream stand in Central Park, and you keep it simple. You offer 3 flavors of ice cream, and then there's just 2 toppings you could have on any given flavor of ice cream, nuts and sprinkles. So drawing out this tree diagram, a person could choose vanilla ice cream, they could choose strawberry, they could choose chocolate, and then once they've chosen vanilla, they could go on to choose nuts and sprinkles. Once they've chosen strawberry, they could go on to choose nuts and sprinkles. Once they've chosen chocolate, they can go on to choose nuts and sprinkles. So that represents all the possible pathways that people have to choosing an ice cream, and each possibility would be following each path. So you could get a vanilla with nuts, you could get a vanilla with sprinkles, strawberry with nuts, strawberry with sprinkles, chocolate with nuts, chocolate with sprinkles. Another way, and a quicker way to find out how many possibilities there are, is called the fundamental counting principle. And it's quicker. The disadvantage is it doesn't necessarily show you what the possibilities are. It just tells you how many. So consider your ice cream stand from the previous example. Let's say the customer had 3 choices for ice cream, just like before, and 2 choices for topping. If I want to know how many total possibilities for different ice creams there are, just multiply the number of choices together. So 3 choices for ice cream, 2 choices for toppings, that's a total of 6 possibilities. And if you remember, that's how many possibilities we had in the tree diagram. Let's say we added an ingredient that our customers could also have. So 3 different types of ingredients: brownie, cookie, cake. Well, it's still 3 times 2 for 3 choices of ice cream and 3 choices for toppings, but you also have to multiply by 3 for the 3 choices for brownie, cookie, and cake. Or in other words, now you have 18 different possibilities of ice creams that you could create for your customer. So let's give example 12 a try. 3 pairs of shoes, 2 shirts, 2 pairs of pants. So how many possible outfits are possible with 1 pair of shoes, 1 shirt, 1 pair of pants? Well, we could draw a tree diagram. Let's try this with the fundamental counting principle, just so that we know ahead of time how many possibilities we should have. So 3 for your shoes, 2 options for shirts, 2 pairs of pants. So this is 3 times 2, which is 6. 6 times 2, which is 12. possibilities. Now the question actually asks you to create a tree diagram, which is what you need to do. I just want to demonstrate to you how quickly to figure out how many possibilities you should have when you're finished. Go ahead and try these next few on your own. Same idea, a lot more choices, okay, but the process is still the same. Alright, sometimes we encounter repetition when we're using the fundamental counting principle. So if we look at this example, license plate possibilities, we've got a license plate with 6 digits, and there are 10 choices for each digit because 0 through 9 can be used. And then anywhere that you want to use a letter, 26 choices are available because you have the letters A to Z. So in New York, the first 3 digits right here are going to be numbers. The second 3 are going to be letters. So there's 10 choices for the first 3 digits, 10 times 10 times 10. Because we can use each of them over and over again. Your number could be 999. And the same for the second 3. You have 26 choices for every one of those. Now multiplying those all together would give you the number of possibilities, which you need to do on your own. Let's change it up a little bit though. In case 2 right here, you can't repeat. So if I choose to use, say, a 7 for the first number in the license plate, you can never see a 7 appear again in the license plate. And the same with the letters. Once I used A, I can't use A again anywhere else. So they start off with 10 possibilities because I could use 0 through 9 for the first one. But after that, there's only 9 because there's one of them that I can't repeat anymore. And then 8. And same thing for the letters. You start off with all 26 letters available, but for each number, there's one less letter available. And then again, you just need to calculate out those possibilities. That's going to be a very large number. But that makes sense. You can make an awful lot of license plates that are unique to the vehicle. Okay, now we've come to what's called permutations. A permutation is just an ordering of objects. So let's take letters A, B, and C. That's one permutation. Another permutation of those letters is just to change the order to ACB or to BAC, BCA. Those are all permutations, meaning we order the letters differently. So that's all a permutation is to order something differently. We could have figured this out using that fundamental counting principle because we know that this is like the fundamental counting principle without repetition. Once you've used an A, you can't use it again for the next 2 letters. So 3 possibilities for the first, 2 for the second, 1 for the third. We just multiply it out, 6 possibilities or 6 permutations. Let's say you had 12 skiers competing in the Olympics. And how many different ways can these skiers finish the competition? Well, once one of them takes first place, okay, all 12 of them could have taken first place, but once one of them does, there's only 11 left to take second place, 10 left to take third place, and so on. A quicker way to write that is 12 factorial. Okay, and then of course you need to calculate that out. That would tell you how many different ways or in how many different orderings those skiers could finish that race. Well, let's change it up a little bit. Let's just say how many ways can they take first, second, and third? Well, now we're talking about 12 of them. Any one of them could take first, but then only 11 of them could take second, and then only 10 of them could take third. After that, we don't care. We're only talking about first, second, and third place. So you'd want to figure that out to get the credit for that point. Which brings us to an equation that will always work. All right, if you want to find out the number of possible permutations of, it should say, an object's taken r at a time. All right, then you put n factorial on the top, n minus r factorial on the bottom. So let's take a look at the skier example we just barely did. There were 12 skiers, and we wanted to take them 3 at a time, first, second, and third. So we're going to say 12 minus 3 in the denominator. Well, that's 12 factorial divided by 9 factorial. So what I'm going to do real fast, I'm going to expand that out. 12 times 11 times 10 times 9 factorial. Those cancel out, and notice we just get 12 times 11 times 10, just like we got right here. So this formula works out really nicely. It's a lot quicker than just writing everything out in an expanded form. All right, let's take a look at an example. You want to visit 10 different colleges, and how many orders can you visit? 6 of the colleges. Well, that's the permutation of 10 things taken 6 at a time. So 10 goes in the spot for N here on the top and on the bottom, and 6 goes in the place of R. So that gives us 10 times 9 times 8 times 7 times 6 factorial on the top and 6 factorial on the bottom. You cancel those out, and you're left with just these, which you can multiply those out to get how many different orders you could visit those 6 colleges. Your calculator can do this for you. So if you go to the math menu, so hit the math button, you'll see the probability menu, and then inside the probability menu you'll see NPR. When you select that, it will allow you to put an N in and an R in, and you just hit enter, and it will calculate this for you, which is nice because that can take a while. It's quite a few keystrokes. All right, last thing, what if you are trying to order things that have repeated objects? For example, the word mom. I could take mom and reorder the letters O-M-M, M-M-O, but then when I go to do it again, I get M-O-M, O-M-M, M-M-O again. I've already listed those. Those are repeats. So there are only 3 distinguishable permutations, meaning they're not the same as any other. When this happens, we have a little bit different formula. We still have n factorial, the number of things. So for example, mom has 3 things, but every one of these Q's down here stands for the number of times that one of the elements is repeated. So let's take a look at the word Ohio right here. We have 4 objects, so on the top we'd have 4 factorial, but on the bottom the letter O is repeated twice, so we would have 2 factorial. Alright, so 4 times 3 times 2 factorial, and in the bottom 2 factorial. 4 times 3, so there'd only be 12 ways. Okay, Mississippi, I'll set this up for you, you'll have to solve it. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 objects there. So 11 factorial on top. But you have several repeats here. S is repeated 4 times. And then P is repeated twice. And then you have I repeated 4 times. Okay, so for every repeat, you have to put the number of times it's repeated. When you calculate that out, you would have the number of distinguishable permutations, meaning ones that were unique. They didn't look like any others. And you'll need to solve that out. Okay, that's it. Let me know if you have any questions. You should be able to do everything on this assignment with that info. So, good luck. Happy mathing.